Hey everybody, thanks for joining me here on this video as we try to make up for a little bit of lost time due to the university shutdown this Wednesday due to weather. We're going to be trying to catch up a little bit on our lecture material, and today our goals are that we're going to try to provide a rationale for those activating, deactivating groups in electrophilic aromatic substitution that we talked about in class, and then also provide a rationale for ortho-para versus meta-directing effects, also in electrophilic aromatic substitution. Ultimately, what our big goal is, though, is to be able to use these rationales to make predictions about reactivity for substituted benzenes in EAS reactions. So when we're able to look at the structure of a starting material, recognize that it's undergoing electrophilic aromatic substitution, and then make predictions about how fast that reaction should be relative to benzene, and where the incoming group should go on the aromatic. Okay, so with that, let's get started. All right, the first class that we're going to talk about are ones that are strongly activating and are ortho-para directing. So let's see, how can we come up with a rationale, or how can we rationalize that type of behavior? So if you go back to our notes from last time, you'll notice that a lot of these molecules had heteroatoms, so nitrogen or oxygen or something like that, attached to the benzene ring, and that oxygen or nitrogen brought a lone pair with it. So let's do an example as we talk about these strongly activating groups. So I will draw on a methoxybenzene derivative. And if we think about how electrophilic aromatic substitution can go on this molecule, let's draw out a halogenation reaction. We could potentially get three different products from this because there are three unique sites on the ring: the ortho, meta, and para positions on the ring. Okay, so those would look like this, where we would have a bromine ortho, a bromine meta, or excuse me, we'll do para first. Or one that is meta. Okay, so the way that we're going to rationalize these effects of strongly activating, so a rate that's faster than benzene, and the major products that we get out of these reactions are by looking at the rhenium ion intermediate. Now, you all nailed this, or most of you nailed this in class the other day when we talked about the rate-limiting step, the thing that is the slowest step in electrophilic aromatic substitution, and that's that first step where the benzene ring is attacking the electrophile, generating that rhenium ion intermediate. So if we think about the rhenium ion intermediates that we would generate for these three different products, they're all going to look slightly different. So let's draw those out. Okay, so for ortho, our rhenium ion that we would draw would look like this. We would have the two substituents, ortho, that's where the electrophile attacked, and now we would have a carbocation. The important thing that I want to call back to are the different places that the cation can exist on the aromatic ring. So we can draw resonance forms to show the delocalization around that ring. So let's do that as well. got one here, and we can draw one more, keeping that cation onto the ring. And these are all analogous to the 3 resonance forms that we drew out when we were just doing benzene in class. But what I'd like you to do is to think about if there are any additional resonance forms that we could draw for this cation. And what I'd like you to do now is work that on your own. So as you're watching this video, now would be a good time to hit pause and think about if you can draw one more additional resonance form to show the delocalization of positive charge in this ion. Okay, I'll wait for you. So hit pause now and draw out that 4th resonance form. Okay, great. So you did it, right? You drew out that 4th resonance form. So let's use our curved arrow formalism on one of these to show how we can do that. I'm going to use red for that. Okay. So one way that I could do that is by picking one of these resonance forms and using the lone pairs from the oxygen to draw an additional resonance form. So if I draw those lone pairs coming down here, I can draw now a double bond between the oxygen and the carbon. What does that look like? So our additional resonance form would look like this, where now the double bond between that oxygen and one of the carbons of the ring is doing something quite important for this ion. If we think about how we rate resonance forms, one of the most primary considerations when we're thinking about which resonance forms contribute the most to a overall structure, our primary consideration, or one of our most important considerations, is whether or not all the atoms in the molecule have completed octets. And if we look at the ones on top, what you'll notice is that these carbons inside the benzene ring that are bearing the positive charge in each of those 3 only have 6 electrons in their valence. There's undrawn hydrogen substituents, so all they have is just those 3 sigma bonds. Same with this one. And this one has a sigma bond to oxygen, but still only 6 electrons around that carbocation center. The nice thing about this resonance form over here is that it allows us to generate a form where all of our carbon atoms and the oxygen all have octets. So if we count them up, there's 4 bonds around this central carbon here, and also 8 electrons around the oxygen, the lone pair, and three bonds for a total of 8. Now I know some people get a little uncomfortable about having to put a positive charge on an electronegative atom like oxygen, but keep in mind the most important consideration for us is that we have completed octets. So this resonance form is providing us with additional stability. So if we think about what this might do to the overall rate of a reaction, if we draw a quick reaction coordinate diagram and remember what this looked like from our start, I used a Me. Let's convert that into CH3 so we don't lose anybody there with the nomenclature. As we are going up in energy to get to this cation, we're not going to have to, this is not going to be as high in energy as our one just with benzene, because in benzene we don't have any oxygen substituents with a lone pair in order to get to an ion where all of our octets are filled. So that means that the energy of our intermediate should be lower, and the hill that we would have to climb to get over in the reaction coordinate in order to get to this would also be correspondingly lower. So if we think about where these all are in relationship to benzene, both this point up here at the top and this point here where the cation is are both lower. So the lower we have to climb those hills, the faster the rate of the reaction should be. So that means faster rate of reaction. Okay. All right, so that's one reason why the methoxy group, this oxygen, should give us a faster reaction. But now let's talk about ortho versus para and meta. Okay, so if we then consider para, again, undergoing this electrophilic aromatic substitution, we should then be able to have an ion that looks like this. Remember, we were doing halogenation. And this provides us a similar type of orientation where we have the ability to use our oxygen lone pairs to draw that fourth resonance form that gives all the heavy atoms an octet again. So let's draw that one out again as well. Okay. In addition to the other two, where I delocalize this positive charge to the positions ortho to the site where the substitution is taking place. So let's draw those on as well. Okay, so there's one of them. And it looks like I missed a lone pair on this other, or one of the electrons in that lone pair. We'll get that in and complete this by drawing our last resonance form. Okay, so again we have 4 resonance forms, and one of them, this one right here, is that extra good one where we have all completed octets. So if we compare this one in terms of energy to what we were just doing with ortho, we would predict that the situation should look really similar. It should also have a lower barrier relative to benzene, because again, we don't have to go through quite as unstable a carbocation, something that we can't have all the atoms having completed octets for in order to get there. If we then look at meta, what we're going to see here is that we don't have that same benefit anymore. Let's try together to delocalize this positive charge, and let's see what other sorts of resonance forms that we can draw with this. One tool that we like to use is the curved arrow formalism in order to help us draw resonance forms. So let's get a red color so we can show the curved arrow formalism again. My cation is right adjacent to the bromine, and I see the double bond over here, so I can start to try to move it around the ring. So there would be one arrow push, now indicating that I'm going to have my cation on the other side. So let's draw that. Okay, that all looks well and good. I can continue to use my curved arrows to try to push this cation around the ring. Now use this bond towards the bottom of the benzene ring. I can move that one over as well. That'll give me a cation also ortho to where the bromine is, but now on the other side of the ring. The net effect here, though, is that I haven't been able to engage the lone pairs. Anything I try to do with those lone pairs, let's give them a shot here. If I try, we'll use a different color for this, we'll use green. If I try to bring them into the ring and show the delocalization of those lone pairs, if I bring them down like so, right, that maybe looks okay. I'm going to have a double bond now between oxygen and carbon, but that carbon would end up with 5 bonds. So I've got to then move the pi bond that's on it. Well, how could I delocalize it? I can move that one maybe over to here. That would put a lone pair on this carbon right here. But I haven't yet been able to delocalize it down to this cation. And I haven't been able to complete that carbon's octet. So if I finish off with these green arrows, I end up just getting to, I'll draw this structure in green as well. I end up getting to something that doesn't actually look all that awesome. I've got a negative charge now on this. I've drawn on the implied hydrogen. My oxygen now has a formal charge on it of +1. I was able to make this carbon-oxygen double bond, but it didn't do anything to really help out this cation here. I'll draw on that other oxygen, that other hydrogen as well. All I really did was separate more charges in my structure, and I would say that this resonance form right here really doesn't contribute much of anything to the overall picture. Let's just say it's not a major contributor. So even though I can get to oddball-looking resonance structures with lots of charge separation, we know from the rules of assessing resonance structures, this one shouldn't be contributing too much because it's got 2 strikes against it. A carbon without a completed octet right down here at the bottom, and separation of charge up here on top. Making everything look pretty horrible. Okay, so if we then go back and then just assess overall, what are we looking at? We're really just looking at the contributions of the resonance forms that I've drawn in black here. These are my 3 major ones, but none of them have a completed octet on carbon. So the barrier to get here and the stability of this cation should be less than the other 2 that we talked about with let's go back for a sec, where we did the substitution at ortho, or we did the substitution at, ortho is here, or the substitution at para here. So in both cases, those should have lower overall energies compared to where the meta-isomer would be. The meta-isomer we would predict would be higher in energy, so therefore the rate of its formation should be slower. So with this one rationale, this electronic rationale, we can combine, or we can explain both the placement of the group coming in at either the ortho or the para position, and the observation that these methoxy-substituted aromatics are faster than benzene. Okay. And we can extend this to any other situation where we have a oxygen or nitrogen lone pair directly attached to the benzene ring. Okay, only caveat is that it has to be, as I've shown you here, directly attached to the ring. Okay, so great, we've done now activating, strongly activating with those conditions where we have nitrogen or oxygen lone pairs. Let's also talk about the other activating group that we talked about, and those were alkyl groups or other carbon groups. The situation is going to look really similar if we have a molecule like toluene. We're not going to have additional resonance forms because we don't have any additional lone pairs in that methyl group to use to draw more resonance. But what we do have, if we do bromination again, what we do have is, I'm going to draw the possible cation intermediates. We could have a cation intermediate resulting from reaction at the ortho position. That would look like this. We could also have a cation if we did the substitution para to that methyl group. And there would be at least one resonance form where the cation is adjacent to the methyl group. However, if we start trying to do the substitution meta, we end up in this situation here. So if we think about carbocation stability, all of these are going to have two additional resonance forms for them. But if we think about how we would classify the ones that I've drawn up here, I would call this cation a tertiary cation because the cation is on a carbon that is bonded to 3 other carbons. Same with this one here, tertiary. However, on this last one where we tried to put the bromine meta to the methyl group, I would call this one a secondary. Let's put that for 2 up here. And look what happens as I try to delocalize the cation around the ring with additional resonance forms. Keep in mind, we can also draw similar resonance forms for the other 2. Okay, so there would be another one, also secondary. And we could get to one more. But this one is also secondary. So we're never able to get to that really stable tertiary carbocation like we were when we did the substitutions, ortho or para. So meta should be slower as a result. Same rationale. It's going to have a higher barrier. It's a higher energy intermediate. Since it's only a secondary carbocation, it's going to have a higher barrier associated with its formation. So the rate for happening at either ortho or para should be much faster than meta. Okay, so that takes us through our activating groups. We can reason by analogy with other groups that we see. We'll do an example like that in a moment. But for right now, we're going to skip the halogens. We'll come back to them in a moment. What I'd like to talk about now is the strongly deactivating groups. So ones in which we have things like carbonyl groups or nitro groups or CF3 groups or things like that. So these are strongly deactivated. These are meta-directing from our discussion today. Okay. So let's do a prototypical one. We'll do nitrobenzene. And I'm going to draw out the nitro group and actually put on my formal charges and my lone pairs on the NO2 group. So there's nitrobenzene. And let's imagine what happens now if this were to undergo a bromination reaction. We reacted it with a bromine electrophile. So again, Br2, FeBr3. Okay, again, we've got three unique possibilities, the ortho, the meta, and the para positions, just like before. But look what happens now when I try to do things at either the ortho or the para positions. I'm going to draw out cations that will contribute to their resonance forms. Let's do ortho. So again, drawing out the whole nitro group. Okay, if we went to the ortho position with our halogenation, at least one of those resonance forms for the intermediate cation would place that one right here, ortho to where the substitution is taking place, right next to the nitro group. Now, I could draw two more, okay, so we know that those are there. We've already done it a couple times. I'd rather not draw all those out again. I'll just say that there's two more resonance forms. But look what's happened to our cation now. It has a substituent on it, but this substituent is not able to provide us with additional stabilization. In fact, this substituent is providing us with destabilization for two main reasons. Okay, first, I just want to point out that we have positive charges on adjacent atoms in this structure. So let's get a little color. So we have positive charge there, positive charge here on the nitro. Okay. Like charges repel. Right, that should be destabilizing to this cation. Okay, let's use a different color and talk about something else that's going on here. Now this was present in our other ones as well when we also had nitrogen or oxygen on them, but we also have an inductive effect. Since nitrogen and oxygen are more electronegative than carbon, right, there's an induced dipole as well, also moving towards the nitrogen atom. That's also withdrawing electron density away from the carbocation. Now in our previous example, when we had an oxygen there, that dipole was there as well, but we were able to compensate for it by giving a pair of electrons back to the carbocation through resonance. Here we can't do that. So overall, this looks like not a very good path. This should be higher barrier. And slow. Okay. Certainly slower than benzene. Okay, if we look at the para, we see something really similar. I could also draw three resonance forms, just like we've done before. Add that bromine to the para position. One of those resonance forms would also have the carbocation delocalized right next to that cation on the nitro group. So the same rationale. Okay, two more forms, just like above. So overall, this should be slow, and the whole reaction should be slow. All right, let's look at now the meta position. If we go meta, okay, now we still end up with that delocalized cation on the ring, but let's draw out our other resonance form in this case and see if we end up in that situation where the cations are on adjacent carbons. So if I draw those out, okay. Okay, here we are. This one looks about the same. It's just now the cation's further away from where the bromine is. Okay, it didn't get any closer, though, to our cation over on the nitrogen. It's the same distance away as it was before. If we go to the last one, we now have the bromine, the cation, on the other side. Again, back being ortho to where the bromine is, but it stayed even farther away now from where the cation on the nitro group is. Okay, so we're not forced to have our lakes so close to one another. Again, if we look at how close they are, they're now at least 3 atoms away. Okay, whereas up above, they were only 2 atoms away, or directly attached to one another. Okay, so in this case, the meta isomer is kind of like our least worst option. We can have to put a cation on this somehow. It's going to be close to another cation on the nitro group, but it's not as bad as the other two. So meta becomes the preferred product. And overall, we can say that the rates for all of these should be slower than benzene. All of them are going to involve putting a carbocation close to the positively charged nitrogen on that nitro group. Okay, so that's our rationale then for why nitro groups are so deactivating and why the groups coming in are meta. Okay, there's a couple other ones in the strongly deactivating group that I want to talk about, or the deactivating group that I want to talk about, and let's think about how we can rationalize them. We had a whole bunch of them today. I guess we'll just be green for this slide. Where we had a CO double bond, and then I'll just put X over here because we had a whole bunch of stuff today similar to this, where X was H, alkyl group, we had a chloride for acid chloride, we had I think a whole bunch of things that we went through today with that. So all of these were also in the deactivating and meta-directing effects. And how can we see how there is like a little embedded cation on this carbon here, right next to the benzene, this one right there. So the way that we might be able to rationalize this would be to say that we can think about, again, that induced dipole. Let's use a different color for this. Okay. The oxygen's more electronegative than carbon, so there should be a partial positive charge on the carbonyl and then a partial negative out on the oxygen. So again, if we were to do electrophilic aromatic substitution, that would put a positive charge on the carbon bearing this group. That would be destabilizing. Another way that we can rationalize it is to draw out a resonance form for this, just a resonance form for the CO double bond. If we do that, we would prefer to give the oxygen a lone pair and put a cation on that carbon right here. So if we're looking at it this way, this puts this into the same type of group that the nitro group was, where there's a cation directly attached to the benzene ring. So we would say that that would destabilize substitution, ortho, and para. using that same rationale that we had on the nitro group. Okay, what about other groups? We had two other ones that we talked about today, I think, that were also deactivating. And let's draw those up real quick. Okay, we also had this one here, where we had a nitrogen, where all of the sites on the nitrogen were bound up into single bonds. That gives the nitrogen a formal charge of +1. So I think you should be able to see where we're going with this. There's a cation on the atom directly attached to the benzene ring. So that's going to force the substitution to go meta, again, for the same reason that a meta substitution would keep the intermediate carbocation from having to be on that same carbon right next to the positive charge on the nitrogen. Okay, one last one that we also talked about today was CF3. Okay, so remembering back to electronegativities, fluorine is our most electronegative atom that we typically deal with in organic chemistry. So the only way that we can really rationalize this is to think about all those dipoles, right, 3 of them, all pulling electron density out towards those 3 fluorines away from that central carbon, leaving us with a big partial positive charge on that carbon, and then correspondingly smaller negative ones on each 3 of those fluorines. So in this case, we just have a large partial positive charge due to all those inductive effects, due to that strong electronegativity of the fluorine atom. And this too is going to basically serve the same purpose as having this positive charge directly attached to the benzene ring. So in both cases, this should be deactivating and meta-directing. Okay. All right, we've got one more class of substituents to go through, and then we will be done. Okay. The last one we're going to talk about is halogens that are directly attached to the benzene ring. So let's talk about if we have, say, fluorobenzene. Okay, so remember that fluorine is going to have its 3 lone pairs with it. What would happen with fluorine if we did electrophilic aromatic substitution on this fluorobenzene? Well, I gave you the answer today in class that it would be ortho-para-directing, but deactivating. And this is kind of splitting the difference between the 2 groups that we've talked about before. So how can we rationalize this? So again, let's do halogenation. Okay, if we went to ortho or para, so by now I hope we're kind of up with the idea that both of those are going to have similar placements of the cations in the ring with respect to the fluorine substituent. I could get a situation, we'll do para, where that cation is on the carbon that is bearing the fluorine. But look what I can do with that fluorine. I know fluorine doesn't really like to share its lone pairs, but I could draw a resonance form using those lone pairs, just like I did with the oxygen or the nitrogen. And even though this fluorine, to give it a mood, doesn't look particularly happy with that positive charge on it, it does still have an octet, as does the carbon it's attached to. So using this as a rationale, I can say that it should favor putting the bromine either para to that fluorine or ortho to it, because I can get to these filled octet resonance form intermediates. So favors orthopara. But it's deactivating. And Why is it deactivating when all the other ones that we talked about that had these lone pairs on them were actually activating? Well, fluorine is our most electronegative element, so if I think about it, and the other halogen's not too far behind, if I think about it, they are also going to have a really strong dipole associated with that carbon-fluorine bond that will also put a pretty sizable delta plus on that carbon just from this dipole alone. And that is what we use to rationalize why they are deactivated slower than benzene. Okay, so I think I've gone through pretty much all the different types of groups that we talked about today. What I'd like to do now is work a few problems with you to see how well we're internalizing some of these concepts. So I'm going to draw one out, and I'd like you to kind of check your knowledge on this. I'll draw out the problem. I'll ask you to make a prediction as to whether or not it would be ortho-para or meta, or activated or deactivated relative to benzene. Okay, so the first one we're going to do is one that is not on our chart from today's groupings. It's one that you haven't seen before, and I'd like you to make a prediction. Okay, so we're going to have a benzene ring, and I'm going to put on a substituent. I'm going to put on a thiomethyl group, so sulfur. And take a quick peek where sulfur is on the periodic table. You'll see it's right below oxygen. So the question for you is, if I did electrophilic aromatic substitution, let's do, say, a Friedel-Crafts acylation this time. Where should I go? Or should my major products be the ortho and para isomers? We'll put them in a box because ortho and para go together. Or should it be the meta isomers? Okay, as I'm drawing these out, you think about it. Okay, if you need to, press pause here on the video and think about your answer. Which way do you think that this one should go? It's okay, I'll wait. Okay, you're back. You made a choice. Did you go with ortho-para or did you go with meta? Well, based on reasoning by analogy from the things that we talked about today, I would go with ortho and para. So, nicely done if you chose ortho and para. So why would we do that? Well, I would say that the sulfur lone pairs should behave a lot like the oxygen lone pairs, since it's right below it on the periodic table. So if I had to draw resonance forms for either of the products leading to the ortho or para isomer, I would be able to use that lone pair to get to completed octets in my intermediates. Those completed octets would provide additional stability to the intermediate and would lead to a faster rate of reaction for the formation of those products. So the solution would be to use sulfur's lone pair to fill octets in those rhenium ions. that predicts ortho-para. Okay, great. Let's do one more, and then I think we will call it a day at this point. So another one, I don't think this one was on our list from today either, but I think you should be able to come up with a rationale for this one. Okay, let's imagine that we are going to do halogenation on benzene sulfonic acid. Okay. So now we're going to halogenate. And the incoming bromine could go either ortho, meta, or para to the benzene, the sulfonyl group. So again, we'll group them, ortho, para. Okay, so there's my ortho isomer. Here is my para isomer. Well, again, we'll put those in a box. Call them ortho-para. Or my meta isomer. Off here on its own. Okay, so if you need some time to think about your choice for this one, go ahead and press pause on the video. We'll be here right when you get back. Okay, great. So you thought about this one a little bit. Which one did you go with? Well, the correct answer this time is going to be the meta isomer. And how can we rationalize this? Let's again think about the structure of the benzene sulfonyl group and see if that can help us provide more of a rationale. I'm actually going to draw out the sulfur-oxygen bonds in this molecule. And I think that should give us a hint. So if I put on my sulfur like so, I've got double bonds to oxygen here, double bond to oxygen here, single bond to an OH group. This starts to look a lot more like those compounds that we talked about where there was a carbon double bonded to oxygen. And each of these is going to have a really strong dipole. Okay. That we talked about before, almost like the CF3 group. I could also draw resonance forms here using that type of rationale where I have a positively charged sulfur. Okay, and now I have that positive charge directly attached to the ring, and it starts to look a lot like the nitro. So, deactivated and meta-directed. So I hope these last two examples have shown you how we can use the principles that we talked about today to reason by analogy and make predictions for functional groups that you haven't seen on your chart. You just have to find the attributes of that functional group that map on to the concepts that we've talked about today, so you can always make a prediction about which way it's going to go. Okay, with that, that brings me right about to the 50-minute mark, which is the standard time for a lecture. So I'd like to close here now and say if you found value in this or if you have any questions about the content that we talked about today, start a Canvas discussion board question about it, and I'll be able to respond to some of those over the weekend. Your classmates may also be able to chime in. Let's continue to try to lift each other up and master this material. All right, thanks for watching. See you next time. Bye.